Good to go.
Okay. Hello everyone. Today I would talk about a macOS malware called Finspy. It's a pretty interesting thing, I think. So let's go through it. It's quite a lot. So who is Fisher? They are a company founded in Germany and they're privately owned. You can think of them just like the Pegasus folks. So they create just cyber related tools and sell it to the government to capture terrorists and cyber criminals. So if if your morals aligns with that, you know where to find them. I usually like to point out their mission and vision. I think it's pretty interesting. The mission is to be one of the trusted advisors for law enforcement and intelligence agencies. So this goes with like every country. So CIA, KGB, whatever. So they want to be one of the best, and that's fine. And the way they do that is provide the first class cyber solution. So like top APT uh, stuff. So a lot of cool vulnerabilities and all that fancy stuff. They try the best to find it and use all of that against organized crimes and to solve world problems. So in one of their campaigns, they had an open server, which was interesting because you would assume that a company like this should have good security, at least for a public server and a server that hosts all their payloads. But that's not the case. They had a Linux server that was publicly available and that had all the payloads. And one security researcher was able to download all of that. And we find there is something called Finspy, which is a malware that is used on multiple OSs. So there's different variants. There's for the Mac OS, Windows, Linux, Android, and so on. But in this case, we talk about the Mac OS one. The Finspy is a spyware that is used again to target activists, journalists, and cyber criminals. Yeah, like I just said a few minutes ago, it's just they had a server that just had all this open, and yeah, let's go into debugging it. So they have multiple variants of this malware, but this is the one I'm using. It's called this name, Kalinia. I honestly don't know how to say that well, but that's the name, and that's what we're gonna go with today. So first thing I do is check the signature because on macOS, any app you create has to be signed with your Apple ID, and Apple has to verify that. And when you do all of that, then anyone can just download your app and it runs smoothly. If not, you would see a pop-up that says, hey, this app was not signed by anyone, or we had no way to check the signature. Are you sure you want to run this? And if Apple detects it's a malware, it just tries to move that to the trash without running it. So I use a tool called What's Your Sign, created by Patrick Wilder. This is he's an ex-NSA folk that really dives into Mac security. So he created this tool that would show you this image on the right, and it just tells you that, hey, this application is unsigned and you just cannot run it. There's also the Apple like dedicated command line tool that does the same thing. It's called Code Design. As you can see at the bottom, it just pretty much tells us the same thing, that the app was not signed. So in order to run this, you have to bypass some other stuff, but that's for another day. So I got the malware from Objective-C, same guy, Patrick Wardo, that got it from his website. And the malware seems to be in a DMG file, which is a DIX file, meaning that you can mount this to your file system and just install it. And that's how most applications are. For example, Discord, if you download Discord on macOS, it's a DMG and you have to mount it to install it. So instead of me actually installing this, I can see that there's an application, and every app is a folder with other files in there. So I was able to just go in there and yeah. when you run like ls on that app name, you would see something like this. In a regular app, you have folders like the contents, the resource, the Mac OS, which contains the actual binary and some other stuff. But as you can see with this malware, there's a couple of interesting stuff. First, there's two binaries, we think, just because of the icon on the left. So we assume these are two installers. And then we see an hidden file, that log, that usually never happens. It just shows that there's something malicious behind the scenes. So, and in there, we can see there's another app. That app just, again, verifies that it's another binary. If you look to the top, you can see there's this folder, the original name, and in there is this other app or this other binary. Usually for malware to really work, so on macOS, for to be a successful app malware developer, you would want to have your malware in the macOS, then have the original app inside of your malicious app, so you can like cover your tracks. So that's exactly what they did. They had the malware here and the original app up here. But we are going to look into this two installers right now. But actually, before I do that, I always look at something called the info.plist. It's like a metadata file that contains some really cool, interesting stuff. For example, it tells us like what binary is going to be executed when you double click on the icon. And as you can see here, well, in this last two images, it shows that the binary or the executable that gets run is the install Kania binary. So we can know that and know that, hey, that's the entry point. So let's look at that first. But also we get some cool information like the machine. So it tells you what OS the malware was compiled on. And in this case, it is 12F45. And if you do some conversion, you will figure that it's the Mountain Lion. So OS X 10.8.5, which is a really old version. I think there's if you want like the ISO for that, I believe it's still public. But that's what the developers used. That was their primarily OS. And it also gives us information about the Xcode. So this was created with Xcode and it has the version. All this information is just more like to build up your case if you have to report this to whatever person you're trying to present this to. Like I said, we found the entry point, which was the install and the long name. But what I did is to run files on it. So still doing like the basic static analysis of stuff. And we can see that the install Kalia file is actually not a binary, but a bash script. And the installer name of the installer is the actual binary. So when you cat that file, we can see a couple of really interesting stuff. First, it runs the Eden file or the Eden application, which I think we'll take a look at it later. Then it goes to sleep for 2 seconds, then deletes itself, then replace itself with the installer app, or the installer binary, then run itself again. So that's a really weird way to just run this installer script, because they could have just done all of this inside of the binary, but I guess they have their reasons for that. So after that, we can look into the app it tries to run, and we can see right away it's malicious, because VirusTotal is usually up to date, and it takes a lot of work off my hands, so I don't have to manually analyze all of these binaries that we're gonna see and just kind of get a feel of what this might be. And just looking at VirusTotal, we can also tell it's unsigned, and it turns out to be another backdoor for another payload. So it seems like this malware is really simple, but yet complicated because of the number of files it just has. So what I did, just keep in mind, this installer is from that, it's from this guy. So still doing like metadata stuff, we run the code design on it, and we can see there's more information about this binary, and we can see the Apple ID, which is again really interesting, good to have. We can say if it's like a regular developer, you would say like their website name, that the name of the project, but in this case it is coverpage.com that blue doom. So again, this might not be really useful from a malware analysis point of view, but it's always good to have this for your report. So we have that information. We can see who actually signed it. So you can see that Apple signed this without knowing that this was going to be used for a malicious intent. But again, just metadata getting stuff. And when we run strings on that binary, we can see really, really interesting stuff. First of all, we see ptrace, and we see this 3 lines here, the VMware, VirtualBox, and Parallelize. Yeah. And just from looking at that, we can just tell that maybe this app or this malware is pretty smart to do a couple of things. It can detect if it's being debugged, and it's trying to see if it's also running in a VMware or in a virtual machine. So just seems like we have to bypass like multiple steps to actually run this malware. So that's an interesting project problem to have. If we look at the bottom, we can see a couple of more interesting stuff, like a path to the Python binaries, or to the Python command line. We also see chmod 06777. So that's a Linux permission number. So there's probably a change of permissions. And up here, we can also see like the chain own and the root colon will, which also we can assume that it's trying to change the ownership of a file to be root. So that's really cool or interesting to see. And just there's a lot of strings, and in the other part we can see there's more, like unload and installer, logged in D, and a bunch of other file extensions. The first part of the unload and Kurtz unload, and the one at the bottom with the .Kurtz file extension, this just tells us that there's a rootkit in this program. So that is pretty, you can see there's going to be a lot of files in this binary. So what we have so far, we can see that this app has the potential to do anti-debugging. It has a virtual machine detection just based on the list of strings we found. There might be some extra scripts to run. And oh, I forgot to point out, there was another string that had the launch CTL and the login d.p list. Usually that will just notify that there might be something with persistence. So something we'll look at. And the last one is the login d.kurtz, which is again this file extension. Just it's a kernel extension for macOS. So still looking at the installer binary, what I did was to extract the function names. So this again, still getting more information about the malware without running it. And we can see some really interesting names. Things like install payloads, expand payload, unload Kurtz, unload agent, and load agents. Just goes to confirm our hypothesis of like this malware doing some kernel stuff or having extra agents. So function names are really good to get. And all of this was using a tool called class dump. And the goal of that is, again, to extract the function name from a Objective-C binary. So all the things you see here are just Objective-C style function name style. Yeah. So time to do some disassembler. So let's look at some assembly stuff if you guys would love to do that. So for my choice for disassembler, some people would use IDA Pro or other stuff. But for macOS related stuff, I rather use Hopper, which was designed to really disassemble Mac related um, Mac or iOS application, mainly the Objective C part of this. So it makes it look more cleaner than IDA or the others would do. I might be wrong with that, but that's my choice of tool in this case. And the main function, we look in the main function. I don't think I have a picture of it, do I? Well, these are all part of the main functions. And we can see all of those targets or the way the app malware is trying to hide itself. First is the deny or the ptrace, deny ptrace. We can see it makes a call using the DLSim. So that's a dynamic library call to ptrace. So it's going to try to detect if the malware is being ran in a debugger. So we can see that part. So that's one method of trying to detect that. Another method it uses is the sysctl. This part, I think it's at the bottom, but it's not there. But the sysctl is similar to the first one, but when it calls this, it returns a flag or returns a value 800, which says that if you get this number, it means you are running in a debugger. So they had two ways for detecting a debugging methods. And the last one, just to verify that you're in a VM, it has this weird shell script that runs. And when you get like the host name or the manufacturer name, if it sees it's VMware VictorBox or the other one, then it's just like, okay, I know I'm in here. I'm just gonna bounce out. So what are the methods? The first way I bypassed the VMware detection was just to edit the binary. And since I was using VMware, I just changed from VMware to MMware. So even though it runs, my machine will still have VMware, but the binary is looking for that MMware and VirtualBox. So it's just going to say, oh, if this is not VMware, I'm just going to keep on going. But the big part is doing some dynamic analysis to bypass the ptrace. So the first way I did to bypass the ptrace was to first put a breakpoint at that exact call, as you can see at this point. So this 1232, which is right here, this is, I put a breakpoint at that place in memory. And instead of going to the next step, which will like run that function, I can just change the program ID or the EIP to be the next instruction. So instead of the malware to run or to call this function, it's just going to just skip to the next one. And as you can see right here, where it says register write PC, I put in the address of the next line, which is 1237. And when I move to the next line or press N, which means step over, it's just rather than calling the deny ptrace, it went to the next line in the code, which is right here. Well, 1237, and it just bypasses the ptrace. So that's one way of bypassing this. Another one is you can, instead of just like moving over or just not calling the ptrace, you can just do a NOP, so NOP, which means no operation. So we can just NOP this address. So when it runs, it just ignores, it doesn't do anything. It just continues going. So that's another method of bypassing this block. The next one is bypassing the sysctl, which I think I actually did, but there was other issues that I was not able to fix on time. So again, the first thing I do is put a breakpoint at that line where it tries to call the sysctl. And again, I'm just going to say this so you guys remember. The sysctl returns a value, and if that value is 11 bits, so if it's 800, it will, that just shows that it is running in a debugger. And in this case, this is the line that I have to try to bypass. So I put a breakpoint like a few lines above the return value and just went line by line till I got to this point. And when I got there, I printed out the value, which was 5806. So instead of using this value, I changed it to 5006, which is still 11 bytes, but 11 bits, but it's not that 800 value code that it's looking for. So when you press next, it successfully go over it. And now I can continue like the next step. I'm just continue to reverse the malware. But when I continue to run it, there was a problem that says bad access. And the problem was in this DYL stub binary, which is the DYL is a dynamic loader. So this was something that I did not look into, but it seems like I was able to bypass the initial problems with the malware. So like the ptrace or the debugger part or in VMware detection, I was able to pass that, but there's just other things in my that I could not fix in time. So this was pretty cool using the debugger for the first time, or yeah, for the first time. So yeah. But if we go back to using the disassembler, there is still some function names that like kind of tells us what is going on. There's a function called the expand payload. When we look into that function, we can see this is the part of the source code. And if you've never done a lot of iOS or Objective-C coding, this might look weird and not have the clue what is going on. But the thing you can keep an eye out for is this part where it says unzip. So unzip, system temp, and compress payloads. Those three words, actually with this one, write to files. Those four words kind of just verifies that this function is trying to extract or unzip a lot of additional payloads. So let's find out what those files are. When still using a debugger, again, I would like to point out that I could not get this to work, but the blog post I was looking at actually had it to work. And this is what the debugger would look like if everything works perfectly. So I would have put a breakpoint in that function and just run it line by line. And as you can see at the last three lines, when you do the x/s, this just shows you what's stored in the RSI, RDI, and RCX. And we can see that it's trying to unzip this line, unzip this folder, arg.zip to this folder. So you can see that the expand function or this, sorry, we can see that this actually makes sense. Let's try to unzip arch.zip to this location in the file system. And when you run that application and everything works perfectly, we get more files. We get helper, helper2, helper3, installer, and so on. So yay, because now we have more binaries to reverse, but it's so much that it takes a long time. Time is going on. So when you run files on this is what we get. We can see they're mostly macOS binaries, but there's one that is a Python list. We can talk about that really soon. And all of the screenshots that I could not get was taken from Patrick Wallard. So that's his name. You guys should definitely look him up if you have the time. So the first binary is helper. Again, we put it into VirusTotal just to get some basic information. And we can see it all points to the Finspy binary, and yeah. And this is the way it launches. This is where it gets slightly confusing. The installer, the binary that we were looking at actually runs this helper, and this is the code to run it. I just wanted to point this out, and yeah. And the goal of the helper is to run a bunch of low-level privilege escalation on the kernel. So if you're using a really old version of macOS, it's going to try to run a few, like 4 or 5 local privilege escalation to be root. And when that doesn't work, it just goes back to a really less complex approach, which is just asking the user for their password. Like what else if your privilege escalation doesn't work, there's always a user to help you. And the way that happens is by just doing a pop-up like this. So if you're ever using Mac OS and you're trying to install something that requires like sudo privileges, it's going to show you this saying, hey, this application wants to make changes. Can you put in your password? So with this, the user will give in their password, and from there, the malware now has root privileges. And anything created by this process or by this app process will have the root user, and will have root privileges. And just to even add more, like to verify they are root and have all the permissions they use those commands that we saw in the strings before, the change honed and the change mod, to be fully sure that they are root users. The output 2 is a Python script that just again does more privilege escalation. This is really interesting because this is a public exploit. So if you look it up, it's a CVE, and this is the exploit for it, and it targets 10.9.5 and 10.10.5. So we can say the target range or the target machines are around this range numbers. So it's always just good to have all of this information. Output 3 is another local privilege escalation that has another public source code. So if you want to understand, or if you're trying to read this, understand how this helper 3 binary is supposed to work, the source code is located at the bottom. And we can see it's trying to exploit the IO audio file, IO audio family on the framework on macOS. So I'm not going to go into details about how that works. So the other file, the another installer, the goal of this guy is to copy over some modules. So this module, this storage framework, is a module, contains modules for C2 communications. So it copies all of this information and stores it in the library framework storage.framework. And anytime the attackers are trying to contact the target, it uses that framework. It also copies something called login-d to this location, and copies the login-d.plist to that location, to the launch agents directory. When you see this is a way to persist on a macOS system. Attackers will move themselves to this launch agent, and anytime you have that in there, every time you like reboot your system or log in again, there's any files in that path will be executed. So for red simmers, that's something you can always look into. And we can see it's doing all the relocation in that installer binary. You can see it's taken from whatever current locations there are to the preferred locations, which are like /library, /private, /system. So like the really directories that most users would not know about or just have no clue about. And if, like in my case, the static this debugger path did not work, so we can use other tools like file monitor. You can think of this as a process monitor on Windows, but this just notifies me if there's any change to any files on the system. So when I run the application, we can see there are a lot of rename. It says rename, but that's just copying over. So we can see that it's copying from the source destination to the destination itself. So that's just another tool I used to just really verify that what this malware is doing. So remember that the installer, this guy was actually copying something called login-d. So when we do like try to extract the names, we can see a couple of interesting names. We can see things like check_running. We can see extract. We can see launch. So we can definitely verify that this binary is intended to be persistent or to be executed on boot time. So the check running function, as we can see, does some just checks if a specific process is running. I don't exactly know what process's name it's looking for, but just based on the shell and the ps.ef, we can see that there's an array of process name that it's trying to check for. And if it finds them, I think it checks if itself is running and other modules. I could not really figure out exactly what it's trying to check for, but that's a really cool function to look at into. The last part is the kernel module. Kernel modules or kernel extensions of macros are become really hard to debug or just to even play with, because macOS has changed the way it allows developers to do so. So nowadays, especially in the new versions, so like macOS Big Sur and the newest one, developers cannot exactly create their own kernel modules. It's not allowed anymore. In order to do so, you have to like talk to Apple and you have to go through some stuff. But as for now, it's only Apple and some special companies, again, keyword on the special, that are allowed to create kernel modules for the OS. But nowadays, it's not available to anyone. The kernel, just doing again some metadata stuff. The kernel module is not signed, so even though it's not signed, it's still not going to run because Apple still goes with every application has to be signed by them for it to run properly or to run smoothly. So if you don't have that, it's going to be a problem for your end users. This is the login plist. Just point out that we can see the program arguments. This line right here, that's the path to the binary login D. So that's the guy that executes every time you reboot your system or login. So that gets executed. Then we can see this key called run at load. That's the line that says, hey, every time you reboot yourself, please run this file. Please run this binary. So this just verifies what I was saying a little bit before. Still looking at the kernel module or the kernel extension, we can see in the first few lines, it's trying to do some symbol or some library resolvement. I don't exactly know what function names it's trying to resolve, but we can see the memory path, and we can just say, we can assume that it's trying to do some system called hijack. So if you've done some Linux rootkit, you would know sometimes you need to hijack the syscall to be able to do whatever you need to do. So on macOS, I believe this is how you do it, but this is out of my skill set for now. But there's another function called the ph hide, which really kind of just, it's pretty straightforward. It just hides a process based on the PID. We can see it just because it says pros_PID. So it looks for that process ID, then it calls the hide. So this is all like pretty much rootkit behavior to just try to hide themselves from the user. Nothing fancy here. And we can see it creates a file and writes to a file in /temp. My assumption for this is that it's a way for the kernel module to talk to something on the user land. So if you're trying to run some commands, and obviously it's not really easy to run code in the kernel module, so you have to have like a user land agents that kind of just like a middleman. So I believe the /temp folder of this file is meant for that. So the command sent by the attacker would be saved there, and the kernel module would take that and just do whatever it's needed from it. So something I wanted to point out too. So again, I just talked about kernel modules trying to talk to the attacker. How would they do that? Since this is a really old malware, it's really hard for me to even like verify network analysis or to do network analysis, but we have other people doing the work for us. And this is a list of modules and a list of commands that they have. And again, as a red teamer, these are just basic attacker move. You need a tool that just does like the metadata stuff. So like create list files, do some audio stuff, some keyloggers. Everyone loves keyloggers. Interesting thing, it has a keylogger for the virtual machine, which I've never actually noticed in right now. That's pretty cool. But for the most part, we like having shells. So they have a module dedicated to that. So this will give them root shell every time they send a command to the CL module. That's the C2 communication. It's really hard to do analysis with this because the server is down, and yeah. So this was pretty quick, but what I've learned during this process, or like sorry, just go back a little bit. What I've learned in this process was actually using debugger. I'm more of a static analysis dude, so I rather read assembly than to run the code itself. Because as you guys remember, there are some times where the payloads or like extra payloads are embedded inside of the binary, so you have to actually like do some dynamic analysis to extract those. So in the time I was doing this, I was able to learn some dynamic tools. So in this case, I use LLDB, but in the future, I'm trying to use like Radar or GDB. But I know there's a list of debuggers out there, but for now, I was able to learn LLDB, which was a pretty cool thing to do. And I think I want to do more of that. But to finish this up, this is the installer process for the malware. When you double click on the application and you do whatever it does, it decrypts the extra payloads into the temp directory. Then it runs the helper and helper2. And if you remember, those two files are supposed to do some privilege escalation if you have a really old version of macOS. So it attempts to do that. And if that doesn't work, it brings up the prompt that says, hey, we need your password. So please give us your password. And that is the third image here. And when you do so, it does more persistent stuff. It copies the modules. So that's the C2 modules. It copies them to the storage.framework. Then it puts in the persistent part of it. So the login d.plist and the login binary itself. So it places that in the /private/user directory and /system/launch/agents/login d.plist. So all of those just verifies its persistence. So that's the whole macOS shenanigans. These are the tools I used. The first one is again created by Objective-C, which I should say Patrick from Objective-C, same as the file module. I also use some macOS dedicated tool like the code design. This one, the class dump, was something I found in my spare time, which is actually really useful. And the last three ones is the operate disassembler for getting the assembly, and using LLDB for debugging related issues. So these are the tools I did. And these are my references. If you guys will want to read more or read much better report than I did, that's the link, a bunch of links for it. So I will post this in the Discord later on. And that's it for me. Do you guys have any questions?
I think I got a question for you, Emmanuel.
Sure.
Why do you say that LLDB is better than debuggers like GDB?
I didn't say that. I just said that's what I used.
Oh, but like, well, okay. So why did you choose that one? Was it just like
Oh, that's
better for Mac OS environments?
Oh no, that's what Apple has by default. That's Apple's modification of GDB. So I just used it because it's just right there.
Gotcha.
Yeah, and also this was the time frame for this project was not a lot, so there's no time to learn to like bring up install a new tool and to fix my environment. I was like, okay, I have to do this quickly, so I just had to use what was already there.
That's cool. what else do you want to like extend this to? Like, what do you want to reverse next? Like, would you have any future projects that you want to talk about?
I do have a list of actual stuff. I don't. 1 second. This is going to be really, really interesting. Okay. So I have this stuff I'm reading right now. You guys can definitely see my screen. So there's this project, or not even a project, it's malware created by a bunch of big agency like that I will not say.
Mhm.
We can see that this is a CIA level malware, and sure, this might be old, but it's always good to like just to understand how government level or government level cyber teams are really going about like creating exploits or creating malwares for targets. And I think trying to just reverse one of their malwares and just go through all of this is really cool to have. Or
Okay.
it's just always good to understand. So that's something I'm looking forward to doing. If anyone is interested in like doing this with me, you can always just find me on Discord. Always happy to help. So
Also, when macOS intro talk,
what do you mean macOS intro
like
talk?
the file system and everything, like how macOS operates.
I mean, it's similar to FreeBSD in Linux. So, I mean, there are some special directories, but I don't think it's enough to be in the presentation, like to create a presentation out of.
Gotcha.
Yeah.
Okay.
In my opinion, there might be people that might find more stuff than I do.
Well, all right, Manuel.